All right, let's continue on with unit number 7, talking about the different states of matter or the kinetic molecular theory. So, in this lesson for today, we're going to be talking about solids, liquids, and gases, as well as phase diagrams. I know it makes everybody very excited. So, let's just kind of do a review of what we talked about yesterday. And so, yesterday we talked about how all matter is composed of tiny particles, and we've known that these particles are atoms, and they're in constant motion. So the amount of motion is proportional to the temperature, and then remember we measured temperature in Celsius, Fahrenheit, and Kelvin. Excellent. So increased temperature means increased particle motion. So the more the particles are moving, the more temperature it has. Solids, liquids, and gases differ in the freedom of motion of their particles and to the extent in which their particles interact. So we have solids, they're very tightly packed. Liquids are tightly packed but freely able to move. And then gases are moving all around. So let's just take a second to kind of review and talk about solids, liquids, and gases. You may have seen this before in another science class, I'm assuming, but we can spend some time kind of going through it. All right. So here we go, taking a look at solids, liquids, and gases. This first one we can look at, we're looking at neon. So this is actually solid neon. Notice the temperature is 14 degrees or 14 Kelvin. So very, very cold. We could turn that into degrees Celsius. And you notice that it's very, very cold, under 0 degrees Celsius, so negative 259 degrees Celsius. And so remember yesterday we discussed the idea of absolute zero, and if you make this thing even colder and get it to 0 Kelvin, so we're going to free this even more. Notice it's a solid right now. All the particles are moving. They're just vibrating. They're not moving freely around, so that's a solid. If I make this thing even colder, get it to that 0 Kelvin, that absolute zero motion, then nothing will be moving. Let's see if we can get it there. So we've got it so cold that it's 0 Kelvin, which is also the same as negative 273 degrees Celsius, and that is absolute zero, where you have no particle motion at all. And so notice neon is typically a gas, and if you can make it so cold that you can actually turn it into a solid. If I want to turn it into a liquid, notice how the temperature increases to negative 246 degrees Celsius or 28 Kelvin. You have all the different neon particles there kind of floating around freely from each other, but they're still connected to each other. There's a couple kind of floating away from each other, but this is going to be a liquid where they're moving around, but all the particles are connected to each other. And so if I want to increase the temperature even more, so by increasing the temperature, it's going to turn it from a liquid into a gas. And then notice what happens with a gas is that the particles all are moving away from each other and then are no longer connected to each other at all. So this is a gas. We're going to spend a lot of time in our unit discussing different properties of gases. And so just kind of taking a look at this, we could say gas. And that's, we could increase the temperature so much that you would no longer have a liquid where they're connected to each other, or no longer a solid where they're connected to each other and not able to move. And so I could look at this in the form of oxygen. So oxygen, if I wanted to have it at negative 160 degrees Celsius, that would be a gas. You can increase the temperature even more to where it would be actually kind of like the temperature that we have around us existing in real life. So I'm going to increase the temperature to about 30 degrees Celsius, maybe 25 degrees Celsius, and that's going to be about room temperature, so 20, 25 degrees Celsius. So let's increase that temperature. And you'll start to notice this is oxygen. Oxygen is a gas at room temperature, and the different properties of the gas is the fact that they are, well, you have O2, so it's diatomic, but they are not connected to each other in the sense that our diatomic O2s are not connected to each other. They're freely floating around, they're bouncing around. That's a gas. If I want to turn it into a liquid, notice that those particles are significantly colder and they're significantly less motion. They are free to move around, however, but they are connected to each other. And versus a solid, they are connected to each other and they are not freely floating. They are just kind of vibrating back and forth, but they are connected to each other. And so main takeaways from this is that a solid, the particles are vibrating back and forth, but they're connected to each other. The liquids, they are connected to each other, but they are free to move around. And then gases, they are not connected to each other, and they are free, able to move around. So as a review of that, here is just kind of this slide. You can go ahead and take a look at that. I'm not going to go through every single thing on here, but if you can kind of pause and see all the different characteristics here, from mass to shape to volume to compressibility. Compressibility is it compressible? Can you tighten it down and make it smaller? Fluidity is just how fluid they are. Rigidity is if it can break or not, or rigid, just how stiff it is. Diffusion is kind of if you go back to a biology class, the fact that your atoms, in the sense, can diffuse through a particular system. And then you have relative space between the particles and interparticle force. So strongest, they're connected to each other, slightly weaker than solids, and then negligible in the sense that they are not connected to each other. So that's just kind of a review of that. But let's continue on talking about gases. And so, like I said, we're going to spend a lot of our time this unit talking about gases. And so gases are very fun. There's lots of different principles and properties of gases. So we're going to talk about gases and gas particles. So remember when we were looking at that diagram that gas particles are moving around freely. When these gas particles hit a wall or hit each other, they exert a force. So just as if you were to hit something, you're exerting a force on it, these gas particles also exert a force by colliding with each other, as well as the sides of a container that they are in. This pressure divided by the amount of area is known as, this force divided by the amount of area is known as pressure. So if I was to figure out, pressure would be equal to the force divided by a certain area. Can't spell area very well, apparently. Let's try that again. Area. So pressure is equal to force divided by area. And so kind of just to illustrate this, let's go ahead and take a look at this. So if I'm looking at this, this is just another example of gas particles. This one is neon. And so neon is floating around. If I can take this, notice there's one gas particle, I'm kind of moving around in a circle. I can take this and throw it against the sides of the walls. You'll start to increase pressure. So you'll look on the bottom where it says P. There's N, T, P, and T. We're going to be looking at that P. That's the pressure. And notice the units for it are M pascals. And so I could take all these particles and slow them down. When they're slower, they're hitting the sides of the container at a slower speed, exerting a smaller force. And it's the same area, so your pressure would be lower. If I take these particles and start to move them up, basically increasing the temperature, when you increase the temperature, they're moving faster. They're going to hit the sides of the wall faster. They're going to exert more of a force, and that higher force for the same area is going to result in a higher pressure. So overall, if you have the same volume, increasing the temperature, increasing the particle motion is going to increase the force at which they are hitting the sides of the container, resulting in increased pressure. And so that's just kind of the general idea I want you guys to be familiar with in looking at gases. So like I said, solids, liquids, and gases. Gases, hopefully we know the idea of pressure, and pressure is dependent upon the force that is exerted. So kind of how fast are those particles moving, as well as the area that they are exerting their force on. And so last thing to kind of discuss today is this idea of phase changes. And so maybe, I'm assuming you've seen these things before, but you have a gas going to a liquid, that is condensation, a liquid to a gas, that is vaporization, which includes the process of evaporation and boiling. So when you hear boiling or evaporation, that is just kind of like a subcategory of vaporization. And then solid to a liquid, that's melting. Liquid to a solid, that's freezing. And then these ones maybe you're not so familiar with is the idea of solid to a gas, that's sublimation, and then gas to a solid, that's deposition. So just some terms for you guys to be familiar with. You can go ahead and take those down. If you want to write those down, that would probably be beneficial to you guys. And then the last thing, so we talked about these phase changes, and now we're actually going to use all these different solid, liquids, and gases and put them into a diagram known as a pressure temperature diagram or a phase diagram. So this phase diagram will illustrate solids here, liquids here, and gases here. And so on the x-axis we have temperature, on the y-axis we have pressure. Hopefully you can read this as if you have the same temperature right here and you increase the pressure, you can actually change from a gas to a solid. or from a gas to a liquid. Or if you're to do the opposite and kind of decrease the pressure, you can actually change from a solid to a gas or a liquid to a gas. And so I'm just going to go ahead over this one. This is for water. This is the phase diagram for water. So some things to be aware of is if I have a particular pressure, I'm going to say this is 1 atm. So standard pressure, so you can get this down somewhere, standard pressure is equal to 1 atm. So 1 atmosphere of pressure. We'll go through a bunch of different units for pressure, but we're just going to say right now the unit for pressure that we're discussing today is atmosphere. And that makes sense because if you look on top of you, if you go outside and look up, there's 1 atmosphere of pressure on you. There's 1 atmosphere, that's standard pressure. So at standard pressure or normal pressure, so this is also kind of like the idea of normal pressure, you could figure out at 1 atm, at what temperature does this solid turn into a liquid? You can go right here. This process right in this point right here is going to be known as the melting. So anything that's happening right here, going from a solid to a liquid, remember we discussed that phase change is melting. So at any temperature here, you go, all right, at 0 degrees, at 1 atm of pressure, my solid turns into a liquid, it will melt. In the opposite way, if it went from a liquid to a solid, it would freeze. So at 0 degrees, at 1 atm of pressure, my liquid would freeze or my solid would melt. So that's just kind of reading this diagram. Continuing on, you have at this normal pressure, we can go from a liquid to a gas, and that happens at this line right here. So this whole line right here will be indicating the process of vaporization, going from a gas to a liquid or a liquid to a gas, vaporization, or the opposite would be condensation. So as you're going through these two different things, going from a liquid to a gas or a gas to a liquid, that is going to be either vaporization or condensation. So this whole line is representative of that, and you can kind of take a look at those different phase changes. If you're looking through the normal pressure at 1 atm, you can kind of see at what temperature that happens. And for water, it's 100 degrees Celsius. Perfect. And last thing to kind of be aware of is the fact that you can change from a solid to a gas or a gas to a solid depending on the pressure. And so this is not going to happen at 1 atm of pressure. You're going to have to change the pressure and decrease the pressure. And then you can kind of see, all right, from a solid to a gas, that is going to be sublimation, or a gas to a solid, that's going to be deposition. And so that can happen at different temperatures and different pressures. So just be aware of the fact that this is temperature from left to right increasing, and then pressure from bottom to top is increasing. And so last couple things on this diagram to be familiar with is, well, basically this is all just showing at what temperature, at what pressure do you have a solid, at what temperature, at what pressure do you have a liquid, and what temperature and what pressure you have a gas. And so we've talked about these different phase changes. So this whole line is melting, freezing. This line right here is condensation, vaporization, and this line right here is deposition or sublimation. So, and then also at 1 atm of pressure, that is normal. And then this right here is known as a triple point. So a triple point, you can have a solid, a liquid, and a gas all existing at the same time. So classic example is not that I can't really illustrate that right now, but you'd have solid ice, liquid water, and steam all existing at the same point where you have the same temperature, same pressure. You can have all three. It's pretty cool. And last thing here is this idea of critical point. Critical point is a point in where the properties of the two phases become indistinguishable from each other. So you'd have like liquids and gases. When you get to such a high pressure, it's kind of hard to decipher the difference between the solid or between the liquid and gas. So use that information to kind of help your understanding of the worksheet, and then let me know if you have any questions. I'll go through this real quick. This is the phase diagram. So just to kind of help you out, this is the phase diagram that's on the worksheet. Hopefully you can figure out that these are solids, liquids, and gases. Remember that normal is 1 atm of pressure. And so just to kind of help you read this, it says, what is the substance's normal melting point? So normal melting point is at 1 atm when it goes from a solid to a liquid. So right here, this would be your normal melting point, 60 degrees Celsius. Hopefully that's helpful. You guys kind of just use that as your baseline, and let me know if you have any questions.